This is a triangular oscillator made around 555 timer. It has linear ramps and boundaries are from 0 volt to 5 volts. Let's study how it works and how it's designed. Hello everybody and welcome to Practical Power Electronics episode number 8. Sometimes you might need a triangular oscillator with linear ramps and from 0 to 5 volts boundaries. And now I present you simple oscillator made around 555 timer. So inside timer, which is a great component, inside we have two comparators, one sludge and buffer, and open collector transistor. And normally we have voltage division, which we can see here, made by resistors, 5 kilo ohm resistors. And the references for the comparator are upper comparator is 2 divided by 3 times VCC, and lower is 1 divided 3 times VCC, like that. And usually it's used so that we have capacitor here and something like this, and we charge these capacitors from VCC and we discharge it. Okay, usually we can make it like this one, and we put here like this one, and oh sorry, we have to add one more resistor. Oh sorry, no. And if this is high, let's say about 100 kilo, and this is 1 kilo, so charging time constant is 101 kilo times C, and discharging is 100 kilo times C. So the voltage here, this point, goes like this. It's not linear, and the boundaries are 2, 3 VCC and 1, 3 VCC. So now the goal is now readjust those boundaries and make it, because this is RC, this is not linear, this is logarithmic, like this one, something like VCC times 1 minus E potency minus T divided by tau, something like that. It's not linear, and our goal is make it linear. Of course, these are fixed values, those boundaries, and the goal is make like this one, from 0 volts to 5 volts, like this one. Okay. And now we can look the schematic. So first thing, we can change this reference point by supplying it external voltage source, which is this one here. It's made by shunt regulator TL431, and we have here 5 volts, and it goes here. So this is not anymore 2 divided by 3 times VCC, now it's constant 5 volts. Okay, next time, this point over here. Because it's not wired out from the chip, we cannot adjust this one. So we have to replace this one by external comparator. So when comparator is external, we can decide or dictate what is the reference voltage. So it's this comparator here, LM311, and this comparator have open collector, but emitter side we can decide what potential we connect this emitter side. So we put it now to G and D potential, and why? Of course, because this 555 timer works between 15 volts and G and D. Okay, next step. Because this is RC charging and discharging, we have to replace R by current source or current sources. And when we have constant current supplying a capacitor, that means that we have constant slope. I is C times du dt, like this one. Okay, we can solve du dt, which is I per C, and if I is constant, this is constant, du dt is constant. Okay, in schematic, here we have one constant current generator. It makes here from 15 volts we have 5.1 volt zener, and here we have threshold voltage. So this voltage is about 5.1 volt minus 0.6 volt, about 4.5 volts. So if we add here resistor, it dictates what current is emitter current, and collector current is almost the same. And so in this case I have 10 kilo ohm resistor, then 1 kilo ohm resistor dictates 0.45 milliamps current, 2 is 0.9 milliamps current. And this current charges this capacitor. So we have linear ramp up. And when it gets to level of this threshold over here, which was 5 volts, 555 reacts and activate this open collector pin number 7, and disables this, or not disable, it turns to current to G and D, not anymore here the capacitor. Okay, now we have similar but reversed polarity current generator, which how do you say, sucks the current out from the capacitor. So now this sucks, but this sucks all the time, and we have here 10 kilo ohm resistor, which means 0.45 milliamp current, but the current here is double. It means for example here we have double current, 0.9 milliamps, and we have here single current minus 0.45 milliamps. So the net current to the capacitor is 45 milliamps plus. Okay, when this one goes zero, then we have minus 45 milliamps. So we have now situation where we charge the capacitors plus 45 milliamps and discharge it minus 45 milliamps. So that's the theory, and next let's look how it works. I have made this schematic to on the breadboard, and we can measure how it works. Here we can see triangle waveform. It's very linear. Frequency is about 5.7 kilohertz, and it starts from 0 and stops to about 5 volts. So it's look just fine. We can measure another things here too for fun. Okay, let's measure here external comparator output. And we can see it here. So here we can see the lower threshold, which is 0 volt comparator output, which triggers this second comparator, which triggers latch. So it's worked just fine. We can see small oscillation here near the edges, but it doesn't matter because the latch activates the first how do you say, first not rising, opposite of rising edge, and after that it doesn't care anymore more the oscillation. And we can see here also it's go very nice to G and D, which is 0 volts, and also very nice to 5 volts. So we can measure, for example, this number 7, pin number 7, which is discharging open collector. Which is somewhere here. So here we can see charging slope, and it's disabled or connected by open collector to G and D during this down slope. So here we can see small difference, which is this. I don't know. See, it's this diode threshold voltage. So I think that's all, and this time, and thanks for watching, and I hope see you in the next video. Bye bye.